Hello, everybody. Welcome you all to the session on operations on the sinusoidal signal, and that we shall see in Python. So, Python is the language that we are coding the program in. Okay, so let's see how we can generate a sinusoidal wave in Python. Okay, and how we can perform different operations on this sinusoidal signal. Okay, the objective here is to understand how to perform these operations in Python. Okay, so Python is something that you all should have installed in your laptops or desktops before you take up this task. Fine. So let's see how we can generate a sinusoidal wave and how we can have different operations performed on the sinusoidal wave that we are generating. So first, what we have to do in Python is what I'm telling you. So you need to have packages. Python is a freeware which is available free on internet. You can download, you can install it for free. But Python does not come with all the packages that is required for a particular task. Okay, so we need to have the packages supporting the task that we want to perform. Okay, so for that we have the two packages here that we want to perform the task of generating a sinusoidal signal and performing some operations in that. For that we have the package numpy and another package matplotlib.pylab. Okay, matplotlib is one package that we need to have. Another one is numpy. Numpy is for dealing with numbers in Python, you can say, and matplot is for plotting the different graphs. Okay, so these two libraries or these two packages, you can say, are sufficient for our purpose. So we have to import this. Okay, and before importing, you need to have these packages installed along with your Python software. Okay, so after that we need to define our x-axis. Okay, so I'll be telling you how to do all this in Python, but before we get into the actual Python platform, I would like to give you the prerequisites for plotting a sine wave. So now we have to define our x-axis. What is our x-axis? In any signals for that matter, the x-axis is always time. Okay, so see this time has to be defined properly. Okay, so in this particular definition of time, okay, we are defining it from np dot. Every time I didn't tell you here, so we are importing numpy as numpy np. Okay, and we are importing matplotlib.pylab as plt. The idea is every time instead of writing it as numpy, I'll just write it as np, and every time instead of writing it as matplotlib.pylab, I'll write it as plt. Okay, so this is how I do. So if you want anything, any function from numpy library, I'll get it by doing this np dot. So in np dot, I have the linear space. This is you should read it as linear space. It says lin space, right? So most of you may read it as line space. It's not line space. You have to read it as lin space because it is linear space. Okay, so this linear space is the function that is available in numpy library, and how we are accessing it by typing np dot. Okay, because that is how we are calling this numpy. Okay, so we have to take this library np dot to access linear space, and in this linear space here the first number says it is the lower limit, the second number says it is the higher limit. So the time axis starts at -2 and ends at 2 is what is the meaning of it. Okay, I'm telling you, we are defining the x-axis, and x-axis for any signal is time. Okay, and for that we are using linear space function, which is there in numpy library. Okay, and what is the space that I'm defining it as? What is the time that I'm defining the time to be starting at -2 and ending at 2, and these are the points that we have from -2 to 2. Now for any plots, okay, if the number of points are more, the plot would be better. Okay, so for example, if you have 100, that means that from -2 to 2 you're having 100 points while plotting. Okay, if you say 200, you're having 200 points between space -2 to 2. That is the idea. And if you don't give this third argument, we can call it as the third argument, if you don't give, if you just give -2 comma 2, it means that the starting point is -2, the ending point is 2, and by default it would take 50 points. Okay, in Python by default it would take 50 points. 50 points is sometimes not sufficient to have a smooth plot. Okay, that's why we need to have more number of points there. So that is this. I'll be like demonstrating all that to you after we have this introduction. Fine. Now, so how to define a sinusoidal signal? Now see here, the sine signal in our signals and systems you could have seen. Okay, so how did we define it? We defined the sinusoidal signal as sine 2 pi t. It's a sine wave. Okay, sine omega naught t maybe is the standard signal. Okay, but we can have sine 2 pi t is one example for sinusoidal signal, but we cannot define it the same way. We have to define it here like this in the Python software. So again, you have to you have a function called sine in NumPy library. Okay, so np dot is what you need to every time give the prefix as. So this is a prefix you need to give, np dot. So from this NumPy library, I'm calling a function called sine. Again, see here, this pi you're seeing, right? This pi is a number which again has to be taken from np. That's why when you're calling pi, you're calling it from np numpy library, and when you're calling a function called sine, you're calling it from the numpy library. So sine has to be like should follow np dot, and the same is applicable for pi also. Pi should also be following np dot. Okay, so these both sinusoidal function and pi, okay, both these are being imported from numpy library. That's why we need to say np dot before we use them. That is the idea. Okay, so 2 star because it is 2 pi, so for pi it is np dot pi 2 star np dot pi star t. So this is how we define a sinusoidal signal in Python. Fine. So then what is this? What is the if we have sine 2 pi t, what is going, how is it going to look like? What is the amplitude? Amplitude is 1 because here in this place we don't have it is a sine omega naught t if you take the standard signal. Okay, so in place of a you have 1, right? So the amplitude of the signal is 1. What is the frequency? Okay, the frequency, let's see this. If you compare this sine 2 pi t with the standard signal sine omega naught t happens to be 2 pi. So omega naught means we all understand it's all 2 pi f naught. Okay, so this gives us f naught to be 1 hertz. So sine 2 pi t is a sinusoidal signal of amplitude 1 and frequency 1 hertz. So this is something that we need to understand, and this we shall try uh, plot using the Python software. Is it okay with you? So now let me take you to Python environment. Fine. Okay, let's go. I'll take you to Python directly. And where do you find Python? So you should, if you have installed Python, you should find this IDLE Python. Okay, if it is on 64-bit, if it is on 32-bit, it all depends on what is your processor. Okay, so just open this by double clicking on that. Fine. So you will have this particular window popped up. So this is called as command window. You see this? You see this symbol? So this is called as command window where I can write my commands. Okay, but where do I type my program? Okay, so for that I need to open something called as an edit window where I write my program. Python script I write, right? So I can do that here. Okay, so go for opening new file if you're opening a new file, or go to open if you want to open something that is already existing there. Since we are doing it for the first time, let's say we want a new file, and this new file is untitled. Okay, and as I told you, first we need to bring in the libraries, we need to import the libraries. Okay, so how do we import the libraries? I've shown you that here. Here we have to import the NumPy library and Matplotlib library. So we shall just copy and paste it over there. So it is that simple. All this is available. Okay, you can just go do this. So let's paste it over here. And before we proceed, it's a good practice that we save this file, okay, with some name, because it says untitled here. So let's save this file by going to save as. Okay, so let's say I'm saving it as sine wave, sine underscore wave. Okay, so this is how I'm saving it. Where you want to save it, okay, you give the path where you want your program to be saved. Okay, so I have saved it as sine wave. Understand it? So next, what I need to do, I have imported the libraries that I wanted. I have imported NumPy library, and I have imported the Matplotlib library. So once you have these two, next what I'm doing, I'm defining the line space. You can take this, okay, and you can paste it over there. You can type it yourself if you're good enough, not a problem. But since you're learning it, since you're all learners, so this I'll provide you there, okay, with this particular video. You can just follow that. So this is the line space, this is linear space. What is linear space telling you? We are defining the what? Time axis. So what is that we are doing here? Let's do the comments here. So for writing the comments, you should use hash. Okay, what is that we are defining? We are defining x-axis, right? So we are defining x-axis, and our x-axis is time, as we are dealing with the signals. Okay, so in this linear space function which we have imported from NumPy library, okay, so we are defining the line space to be the time space, rather the time to be starting at -2 and ending at 2 with 200 points. Okay, so I'll come to this 200 points to make the things clear to you. Then you will appreciate what that 200 means here. Fine. So this is how I define the line space, the time space, or the time, the x-axis. Then let's define a signal. Okay, so for defining signal, we can take this. Fine, and let's go here. Fine, we have two spaces, mind you. This is your command window, you can say, and the window that I'm showing you here, this window. So this window is your what edit window, where you are writing your program. So let's paste the sinusoidal wave that I want to generate. Okay, so what am I doing? Let's give the comment again. So what am I doing? I'm defining the sine wave. Okay, I'm defining the sine wave. What is the amplitude of this sine wave? The amplitude is 1. Okay, and the frequency is 1 hertz. I've told you, I've shown you here why the frequency is 1 hertz. See here how the frequency is 1 hertz. I've told you, I've taken sine 2 pi t as the signal, and if you just understand this particular computation, you will understand the frequency is going to be 1 hertz. Fine. Now we need to plot this particular sine wave. Okay, so we need to plot this. So how we can plot is what we need to understand. It's a simple stuff. Okay, so I'll show you that here. I have even the provision for that. I'll just take this set of codes. I'll tell you what these codes are for. Okay, and just paste it over here. Fine, and you should understand that it will give a problem. It will give an error if you have left the space here. So you're not supposed to be leaving space here anywhere unnecessarily. Okay, so you should start from the beginning. Okay, you cannot start somewhere in between in a particular line. Fine. Now plot. Okay, so why this is plot dot? We are using matplotlib, right? So in this matplot library is used to plot the graphs. Okay, so for plotting the graph, what we are doing, we are see here we are using a function plot, plot, which is there as plt in matplotlib. So see, matplotlib is being imported as plt. So this is a matplotlib library, okay, in which there is a plot function. So using this plot function in matplotlib library, so I'm plotting this sinusoidal wave. And this sinusoidal wave, where I have stored that sinusoidal wave is stored in y, variable y. So see here in plot, we give the x-axis, okay, separated by comma, then the the x-axis and the y-axis separated by a comma. So what is a y-axis? Y-axis is supposed to be my sinusoidal signal, and that is being plotted over time t. Okay, and at the same time, what we can do, we can name the x-axis by using x-axis label. Okay, using plot dot. Again, that x label is a function that we are using from matplotlib, and y label is also a function that we are using from matplotlib. Okay, so this is what we are doing. So let's go here. There is some problem. All these labels should come in green, otherwise there is some error you should understand. Okay, so the colors also you should be aware of, so it would help you. So now what we need to do, we need to run. So when I say run, it will say whether you want to save. Yes, I want to save before I run this. So this is being run. So see here, so we obtained now, we obtained the sinusoidal wave. So it is starting at 0, and at 0 the amplitude is 0. Okay, now like from where to where is one cycle? From where to where is one cycle? So that I want to understand what is the frequency of it. Understand? See the time now. We had defined our time to be from -2 to +2, right? And the amplitude is 1. This is something that it comes by default. This we are not defining. Okay, the y-axis is not being defined, the x-axis is being defined. Okay, and we define the time axis, and we define it to be starting at -2 and ending at 2 seconds rather. Understand it? This is how the sinusoidal wave looks like. But how can we make it better? We can make it better by bringing in the grid. Okay, how we, if we want to, if we bring in a grid, what happens? So how to bring in grid? See here, I can take the grid like this. Yeah, so you can go, you can plot the grid by doing this. Maybe I'll do it this way. We can use another function to bring in grid. So that's plt dot grid plus plot dot grid. I hope that's the function to bring in grid. Yeah. See, again, that grid function is available in the matplotlib. So you can just say grid plot plt dot grid and the parenthesis with nothing within. Okay, so it will give you this. Now we can easily see here the amplitude is 1 volt. Okay, on the positive side, and on negative side it is -1. And what is one cycle here? Here it starts at here. Now you can rather, if you want to see it properly, you start at 0. So somewhere here it is 0, and it ends, this particular cycle ends at 1. So that means it is 1 hertz. Okay, and since I've taken the scale from -2 to 2, the time scale from -2 to 2, how many such 1 hertz signals can accommodate, can be accommodated? So it's 1 second, right, from here to here. So if you from one cycle is 1 second, so that means inverse of that is frequency. So inverse of 1 second is 1 hertz. Understand that? So how many such 1 hertz signals can be accommodated within the time scale of -2 to 2? So how many seconds are there? 1 second, 2 second, 3 second, 4 seconds. So there are 4 seconds that we have defined our time scale to be. So in 4 seconds, we can have 4 such waves of 1 hertz frequency. So this is how we need to understand that this is a sinusoidal wave of frequency 1 hertz. Understand that? So this is just one wave. Fine. Now what I can do, I can bring in many such waves with modified versions. Okay. So what I can do is something that you have to see now. Okay. So let's see this now. So now if you bring in another signal here, if you bring in another signal, what happens? I can rather plot that also. Okay. How can do that? Let's say I'll say it is y1 is your second signal. Okay, so let's copy the same signal. Okay, and let's vary that with some thing there. Okay, now see here it's 2 pi t, right? So let's bring in minus here. So how to bring in minus? If I do minus t, what happens? If I bring in minus to this time axis, what will happen is what we are looking at. So not able to see that. Why you're not able to see that? I just declared it. I just defined it, but I have not done much to plot it. So what I can do here, you can take another plot, Control C, okay, Control V. You're plotting y1 here. Now let's run. See here now. So what did I do by giving -1 there? I just have what? Taken the reflection of the signal. So if you take reflection of the signal, what's going to happen? This is what is going to happen. The blue one is sine 2 pi t. The blue one is sine 2 pi t, whereas the orange one is sine 2 pi minus t. So that is reflected version. So if reflected version is always 180-degree out of shift. See here. So if you do this, you will get the plot on the in the same window. Okay, in the same window where the plot is, you will have both the plots. So this is where. So see always on your bottom of your display. So this is what is the symbol for figure. Okay, and here you will have the command window as well as the what the edit window where we write our program. Understand that? So this is how we can have different operations. Now instead of having it in the same plot, instead of having two graphs or two signals, two different signals in this same graph, we can rather try have these two signals in two subplots. Okay, so instead of going for plot, we can actually go for subplots also. So how to go for subplots is something that we are going to see now. Okay, so let's go with this now. Everybody just see here. So this is what you're supposed to be doing. Okay, so let's define figure and how many figures we need, how many subplots we need. Okay, we need two subplots. So this is accessing. AX means you should read it as access. So access to subplot 1, access to subplot 2. So plot subplot. We are having two subplots, right? So 2 comma 1 means we have 2 rows, 1 column. So 2 rows, 1 column means we have two figures sitting one below the other. Understand that? So first row we have one plot, the second row we have another plot. Is that okay with you? Okay, so that is how this plot would be. Fine. Then what is that we are doing in the first plot? We are plotting y1 versus t. Okay, and we give the title to that. We give x label and y label. Similarly, the second plot. So how to take the second plot? So access to plot dot plot t comma y2. Here we can bring in the plot for y2. Okay, I'll show you how it works now. So let's take these codes. Okay, let's go paste it over here in the edit window. Fine. Now you can just make all these as comments. So how to make the comments? Go to format. Go to format. There is a provision for making all the lines as comments at once. Okay, so you can use comment out region. So selected regions are made as comment. So you can place it aside instead of deleting it. It may be of help to you later on. Okay, so just place it aside. Okay, and along with this, what we have here, as I'll just show you. I think I missed this. Plot show is something that is needed here also. So let's keep that out of. Let's not comment this. What happened? I don't know. Plot show is what I missed there. Plot dot show. Okay, so you can bring in that plot dot show here. So that has to be there if you want to show a plot. Okay, now let's bring in this. Okay, figure to have. Now this is something that I'm doing to have subplots. Fine, all these codes will be provided to you with this video. Okay, you can use them. So we're having two subplots now. So the first subplot, the second subplot. X access to first subplot, access to second subplot. Okay, this is how. And these are two rows, one column. Okay, so that means two rows you have and one column, one below the other you will have like this. Fine. And constrained layout true. What is the meaning of this? So that means if you have too many subplots, sometimes what happens is the title that you give to the subplot or the x-axis and y-axis that you define sometimes gets overlapped like this. Okay, so to avoid that overlapping and to maintain proper spacing between the subplots, this is the function that you need to constraint underscore layout equal to true. This is something that we need to follow. Okay, this is a good practice that we have to follow. Understand? Without this also it will work, but your subplots may not be properly coming there. Okay, so they may be overlapping over one another. Okay, so to avoid that, to give proper spacing between the subplots, we use this constraint underscore layout equal to true. So this particular thing. Okay, you need not have to remember this every time. Okay, it is provided to you. You just copy paste, and when you get used to this, okay, you may write your own program without actually looking into anything that we provide. Fine. So next, what is that you're going to do? We again go here. Okay, just copy this. So this is the second thing. That means what is that we are plotting here? Okay, so if you run without saying anything, also it will come. So I'll just cut this. I'll say run. See, it is giving us two subplots like this. So it's the same figure, but you have two subplots. One is this, the other one is this. So this is what I meant, one below the other. Fine. So this is what is going to happen. Now, yeah, let's bring in that now. So this is the first plot. So what would be there in first plot now? See here, first subplot. So this is what is going to be there in first subplot. Understand that? Now, there is no grid in this. So let's bring in grid also. To bring in grid, what we need to do? Okay, see here, just this needs to be used there. Axis 1, okay, needs to be given the grid. So where I can show, where I can say that, I can say that here. So now, earlier the grid was not there. See, this is how the first subplot is. So what we shall do to this first subplot? Okay, we shall just bring in the grid. So again, rerun the program with that grid option. See there, the same subplot is coming with the grid. And what is the signal that we have? See, the 0 is here. So from here to here, it is 1. So it is coming inverted. Why is that? It is going, what happened? Let's see the code. So I'm going with y1. That's why it is so. Let's make it as y1 and this as y2. Okay, the second signal is the first signal. Let be y1. The first signal be the second signal be y2. The first signal be y1. Okay, so let's run it now. See, it's a sinusoidal signal. That is what I have given these here. The title of the subplot is sinusoidal signal. You can just see here. Okay, and the x label is time in seconds, and y label is sine 2 pi. This is supposed to be sine 2 pi t. Understand that? So this is sine 2 pi t. Let's I can do that rather. Sine 2 pi t. Okay, so I can run that now again. So it comes as 2 pi t there because we are plotting sine 2 pi t. That's why. Okay, so we can have the second subplot also. To have the second subplot, what we can do, you can just copy this thing, Control C, okay, Control V, fine. You have subplot for y2. So this is your y2 signal where the time axis is negated. That means I've multiplied time by -1. Okay, so it gives you the reflected signal. Fine. So that's our y2. And what shall be the title? Reflected sign, we can say. We can call it as reflected sign. So that is what we are having here. So here it's sine pi minus sine 2 pi minus is what we are having. So let's run this now. Oh, it's again coming there. It's there only. Why? I did some problems. See, I didn't go for axis 2. I'm doing it on axis 1 only. See, if you do it on axis 1, okay, though we have a provision for subplot, it gets plotted in the same subplot because axis 1 is what we are again going with for plotting the second signal. So this needs to be 2. Okay, so you need to be careful when you do copy paste and do the necessary modifications there. Okay, let's now run that. Now it comes in the second subplot. Okay, and if there are any errors in this command window, those errors would be shown. For example, let me do this. Suppose I make a mistake with this. I'll not type plot. So this is a typo error. Okay, and let me run that now. It gives that problem. Okay, it says in line number 17, in this particular line, it says access to. Okay, PLO is there, which is undefined. There's nothing like that. Is what has no attribute like PLO. Okay, the subplot, the access subplot has no attribute like PLO. It says so. You need to go to line where PLO is there and correct it to something that is available. Okay, so that is how I can do. Now you get it right. Fine, both are coming with grids. And one more thing that I can tell you is you can run the program. Okay, you can cancel this. You can close this window where we are having plots, and you just have this command window here. You can see this what time what we have defined. See, if you just press T, and it will give you 200 points. 200 points it is giving. Okay, so I didn't talk about these points, right? So what happens if I remove this? Well, I've removed that. Okay, let me try plot it for you now. Okay, see, you see the what the sine wave, sinusoidal wave that you're getting. It's not very smooth. Okay, the plot is not good. You can say the sinusoidal wave is not as good as it was earlier when we were taking 200 points. So that means here by default it is just taking 50 points now. See, it is 200 points. You can just see it's giving you 200 points. Okay, now I'll just cancel this, and for this run I'll just give you another T. Okay, I'll type T here. Here we just have 50 points here. 50 points, how we can calculate, how we can see 1 2 3 4 5. So 5 points you have in one row. Such how many rows you have? 2 3 4 5 6 7 8 9 10. So 10 cross 5. So it's 5 cross 10 rather, or 10 cross 5 rather. So 50 elements you have, 50 points you have. Okay, so with 50 points, this is what is possible. What is possible here? This is what is possible. Okay, you don't get a good quality sine wave because you're just considering 50 points between -2 to 2. Okay, so if these points are increased, okay, from 50 to say 100 points. Okay, so let's see the plot. See, the plot is fine, but if you see it properly, it's again not very smooth. You can see some what discontinuity we can say, or it's not as smooth as we want it to be. Okay, so 100 points, 100, taking 100 points is fine, but if you observe it very neatly, okay, it's not as good the signal as it was when we had considered 20 points. So let's just leave this and go with 200 points. Okay, so with 200 points, the plot is really good. So yeah, this is how the things go. So now it's much smoother, much smoother. You cannot see those fluctuations here and there, or the discontinuities here and there. It's very smooth plot. Okay, that's because you have considered more number of points between this -2 and 2 seconds. Fine. So this is another thing that I wanted to show you. Fine. And one more thing, if you want to see this, okay, what is that? If you want to see what your T is, suppose if you now uh, type T and enter, it will not show you that because you have your what plot uh, open here. So if you close this plot, then only you can see this axis T, all the points over axis T. Understand that? Okay, so just remember that. Fine. Now we can have many such operations performed. I have one such file with me where I have performed all those operations. I'll just open that. Okay, so that file is this. Fine. And here also I have maybe I'll take all these off. Okay, and I'll uncomment this. So for uncommenting, what you have to do, you have to go to format and say uncomment. Okay, and bring that here. Fine. So in this, what we're doing, just understand, we have y1. Okay, y1 is the sinusoidal signal sine 2 pi t. Y2 is sinusoidal signal wherein the time axis is multiplied by 2. Time axis is multiplied by 2. Y3 is time axis divided by 2. And y4 is your reflected signal. It's multiplied by -1. And how many plots, subplots I need? I need 4 subplots, so that I'm naming as axis 1, axis 2, axis 3, and axis 4. And I say 4 comma 1. 4 comma 1 means what? I have 4 columns. Sorry, I have 4 rows and 1 column. That means you'll have 4 subplots, one below the other. And what is the first subplot? Is your sinusoidal signal. Second signal, that is y2, wherein I have multiplied the time by 2. So it's a compressed signal. Okay. So if you divide it by 2, if you divide the time by 2, it is going to be an expanded signal. That is your signal 3. Okay. And signal 4 is your time deflected signal. So let's run that and see what we get. Okay. See here, beautifully we have all the 4 subplots here. This is the sinusoidal signal. We have given it the title as sinusoidal signal. Okay, then the compressed signal. Why it is compressed signal? It is multiplied by 2. Okay, expanded signal divided by 2. Time is divided by 2. Okay, this is time multiplied by -1. So this is reflected signal. See here at 0 it is going positive to 1, whereas at 0 here it is going negative to 1. So that means they are time reflected signals. The first signal y1 and the last signal y4 are reflected. They are out. They are 180-degree out of shift, out of phase. We can see. Understand that? So this is how we can get different subplots. Okay. So here we have just shown you how to operate on a signal. That's the sinusoidal. If you consider a sinusoidal signal, how to generate a sinusoidal signal. Okay, and how to have different operations on that is what we have seen now. Okay, so here we have taken 100 points. You can take 200 and make your signal better. Fine. So in the next video, let's try get the different basic signals. Let's say how to have a unit step function, how to have an impulse function. Okay, and we can also try bring in a ramp, okay, unit ramp. So all that we shall do in our next video. And this is something that is continuous, I showed, right? So you can make the same plot go discrete also. The option is very simple, just one change that you have to make. See here in this program, you're saying it as plot, right? So instead of saying as plot, if you say stem, STEM, so it becomes discrete. Okay, so let me just show that. So what I've done, the first subplot is stem and all other subplots are plots. So if I say plot, it is continuous time. If I say stem, it is what? A discrete time. So let me show that by running it. See here, the first subplot is you have different samples. All those samples are rather very close. Okay, because we have taken too many samples. If we reduce the number of points between -2 and +2, okay, you can see that better. Maybe I'll just leave it to be 50. If I take this off, okay, by default it is 50. If you write 50 or don't write, also it takes 50 points. So if you take 50 points, it would be visible to you more clearly the different samples, but your quality of the continuous sinusoidal signal will reduce. Okay, this continuous plot will not be good with 50 points, but you can see the different samples here if you say stem. So if you just take, if you just substitute or replace this plot by stem, okay, you will have a discrete plot of this particular signal. See, all the plots are being replaced by stems. So plot is being replaced by stem. Okay, so what happens if I do that? So you'll have this. Okay, it looks very beautiful, the discrete time signal. Okay, and in compressed version, what happens? I've told you. Okay, in compressed version you'll be losing on samples. Okay, so that's why you have lesser number of samples in compressed signal. So it's not advisable to go with compression of the signals in discrete time, because you lose samples existing at what the at the instance which are not at integer instance of time. So the samples which are not there at integer instance of time, say 1.5, 0.5, 2.5, all those samples you will lose. So it actually results in losing the information. So this is not advisable doing compression of the signal in discrete time. In continuous time, it's fine. Okay, because in discrete time you have the samples only at integer instance of time. So those which are not at integer instance of time will be lost. Okay, so that's why you're finding less number of samples here. Fine, this is possible because you're having stem in your code. Okay, it's just that. So if you just replace the word plot by stem, you will have that. And when you're going for discrete plot, limit it to 50. Okay, when you're going with continuous plot, Okay, see here, I'll make this as 100. Okay, I'll make this 100. You will see more number of what samples there. See, the number of samples are increased. Earlier we had just 50 samples to deal with. Okay, from -2 to 2. Now we have 100 samples between this particular duration. Fine. So this is what I had to give you. Fine. Practice this and learn how to create a sinusoidal signal and operate on that. How to get a continuous time signal and a discrete time signal. Okay. Hope you have understood. Fine. Follow this. The codes will be provided to you. Fine. You can just copy that and paste and see the different operations and the results. Fine. I've just shown it for sinusoidal signal. You can do it for other signals also. A lot of support material is there online. Okay. So you can make use of that. Fine. So with that, we shall end the session. Hope this is of help to you and it would help you in your future endeavors. Thank you.